Lesson 8. In this lesson, we'll talk about section 3.5, which is called the epsilon delta criterion for continuity, and section 3.6, which is about monotone functions and inverses. In this lesson, we'll focus on monotone functions, and we'll leave inverses for the next lesson. We'll start with section 3.5, the epsilon delta criterion for continuity. Let's begin by giving the definition for this criterion. A function f from a domain D into the set of real numbers is said to satisfy the epsilon delta criterion at a point x0 or x0 in the domain if for every epsilon greater than 0 there is a delta greater than 0, so that the distance between f at x and f at x0 is less than epsilon. Whenever x is in the domain is chosen such that the distance between x and x0 is less than delta. Whenever you see something like this, or like this, where you have a difference in absolute values, you should think about it as a distance. The idea here is that we're trying to force the distance between f of x and f at x0 to be as small as we want. So this is true for every epsilon. An epsilon greater than 0 is specified, and we want to find a delta greater than 0 so that the distance between the output values, f at x and f at x0, is less than that specified epsilon whenever x is a point in the domain so close to the original x0 that the distance between them is less than delta. Let's look at a picture. Suppose that this is a graph of our function. Maybe instead of x, this should be x0, but other than that, this is the picture that we're looking at. Let's make these x0s. There we are. So we have some function here, and this is the graph, y equals f at x. And the idea is that we're looking at this point, x0, and we want to know if the function satisfies the epsilon delta criterion there. It's not enough to look at the point x0, we have to look at the output as well. An epsilon greater than 0 is specified, and then you're looking at this band here. You're looking at all of the values, all of the output values, or all of the numbers that are within epsilon of the output values. So the question is, is there a way to say that for all x really close to x0, all of the output values are in this band that you see here? And the idea is that you want to find some delta. So here delta is greater than 0, and we can choose it. And we want to choose it so small that whenever you pick an x from this interval here, this interval about x0, if you pick an x from there, you want to make sure that f at x is within an epsilon of f at x0. So this is our f of x. So that's the basic idea. The epsilon is given at the start, and this is, you can think of as your error term. And you want to choose a delta, which is a distance away from x0, so that any time x is within delta of your original x0, then the output value must be within epsilon of your original output f at x0. That's the idea behind the epsilon delta criterion. Not every function will satisfy this at every point. If we look at this example, and again, really we want to think of this as our x0. This point, x0, is a point where the function leaps from one curve to another. So this is y equals f of x. There are two pieces to this function. there's a definition for all x less than or equal to x naught, and then there's another definition which seems to be used for all x greater than x naught. So what about at x naught? This function does not satisfy the epsilon delta criterion there. We can choose an epsilon so that no matter how close you look to x naught, there will always be some output which is outside of that band. On the left side, we're fine. If I pick an x in here, so if I pick an x within delta of x naught on the left, then the output value is within the epsilon band. However, if I pick an x to the right of x naught, and it doesn't matter how close I am to x naught, then the output is always too large. It's outside the epsilon band. And it doesn't matter how close I look. The measure delta, the number delta, is a measure of how close you are to x naught. You want to choose delta so small that as long as you're choosing x values within delta of x naught, your output values are forced to be within epsilon of f at x naught. But here in this picture, it doesn't matter how close we are to x naught on the right. The output values will always be too large because they'll be up here outside of the epsilon value, or outside of the epsilon band. Let's look at an example. Show that f, defined from the set of positive real numbers, or I should say the non-negative real numbers, into R, defined by f at x equals the square root of x, the square root function, satisfies the epsilon delta criterion at every point x0 in the interval from 0 to infinity, including 0. So how's this going to work? Suppose that x is greater than or equal to 0, and we want to measure the distance between the square root of x and the square root of x sub 0. So that's the absolute value of the difference. We're going to play a little algebraic trick with it. This is our original term, and you can see it here too. And we're multiplying it and dividing it by the same thing. So we have the square root of x plus the square root of x0 divided by the square root of x plus the square root of x0. Of course, everything here is still in absolute values. But we can multiply by that and divide by the same thing because really you're multiplying by 1 in that case. So what's the objective of this? What's the point? Well, if we multiply the numerator together, the two terms in the numerator, you get x minus x naught. This is essentially the difference of squares. You're thinking of this as the square root of x quantity squared minus the square root of x0 quantity squared. So that's why you end up with this. In the denominator, both of those terms are positive because the square root function is defined to be the positive square root. So we don't do anything there, we just drop the absolute value signs. However, notice that the square root of x plus the square root of x naught is necessarily larger than the square root of x naught, again because the square root of x is positive. So if the square root of x plus the square root of x naught is greater than the square root of x naught, then if you look at the reciprocals, you'll have the reverse inequality. 1 over the square root of x plus the square root of x naught is less than 1 over the square root of x naught. Now we're allowing for the possibility that x is greater than or equal to 0. So this might be inequality. Perhaps at this point we should just make sure that we're not dividing by 0, let's restrict x naught to not being 0. So let's just not include that as our endpoint. Let's just not include that endpoint. So what that means is we're going to have that x0 is not equal to 0. Because we want to make sure we're not dividing by 0 in this step right here. Okay, so what have we got? We've shown that the original difference, the square root of x minus the square root of x naught in absolute values, is less than or equal to the absolute value of x minus x naught divided by the square root of x naught. Okay, so what does that mean? If we choose x minus x naught sufficiently small, or let's say if we choose this to be less than delta, then that means our original square root of x minus the square root of x naught in absolute values is less than delta over the square root of x naught, as you can see here. So what that means is we have some control over the size of the difference in the output values, because we know that by choosing x sufficiently close to x0, we can be sure that the difference between the square root of x and the square root of x naught is as small as we want it to be, because we can just choose that delta to be anything we like. So if epsilon greater than 0 is given to us, we choose delta to be equal to epsilon times the square root of x, or the square root of x naught. And if that's the case, then the square root of x minus the square root of x naught in absolute values is less than, well, what is it? It's less than this quantity, but that's less than epsilon, well, actually it's equal because we're choosing delta to be equal. So this is equal to epsilon over the square root of x naught divided by the square root of x naught. And those square root of x naughts cancel and you're just left with epsilon. So, since this was an inequality here, what we've decided, or what we've shown, is that if x minus x naught in absolute value is less than delta for this particular delta, for that particular choice of delta, then the difference of the output values is strictly less than delta over the square root of x naught, but that is equal to epsilon. So what that shows us is that if we insist that x minus x naught is less than this delta, then that means the difference in the output values must be less than epsilon. And this is true for any of these x zeros that we picked, as long as we stayed away from 0. We could also do it for 0, but I just didn't want to divide by 0, so I made that restriction in this case. So what happens next? What does this mean? We know that f satisfies the epsilon delta criterion at x0, so what good is that to us? That leads us to this theorem, the epsilon delta continuity principle. A function f from d to r is continuous at a point x0 if and only if f satisfies the epsilon delta criterion at x0. Or to put it more precisely, a function f is continuous at a point x0 if and only if for every epsilon greater than 0, you can find some delta greater than 0, such that if x is any point in the domain, such that the distance between x and x0 is less than delta, it's necessarily true that the difference in the output values is less than epsilon. So this is a characterization of continuity. We defined continuity in terms of converging sequences, but there's another way to think about continuity, and you can think about it in terms of the epsilon delta criterion. So a function is continuous if and only if it satisfies the epsilon delta criterion at that point. Let's look at the proof. We wish to show that a continuous function satisfies the epsilon delta criterion. We will show this by proving the contrapositive. So, suppose that f does not satisfy the epsilon delta criterion at some point. Notice there's some space here. Let's fill in the details. Let's remind ourselves what it means to satisfy the epsilon delta criterion. We have it written right here. It's this business right here. So let's write that down. F satisfies the epsilon delta criterion at x naught in D, provided, well, let's write it down. For every epsilon greater than 0, there exists some delta greater than 0 such that the distance between the outputs is less than epsilon whenever the distance between the inputs is less than delta. But let's write that in a slightly different way. We're going to write it this way, so that the difference between x and x naught being less than delta implies that the distance between the output values is less than epsilon. So the way we said it earlier was that the condition on the outputs is satisfied whenever the condition on the inputs is satisfied. Another way of phrasing that is that this condition on the inputs implies this condition on the outputs. Now, why did I write it like this? My goal here is to write out the contrapositive, because that's what I want to prove. That means looking at the negation of a certain statement, or in this case, two certain statements. And so what I want to do is I want to write it out as a logical statement using symbols. So this criterion here can be translated into logical symbols by saying that for every epsilon greater than 0, there exists a delta greater than 0 such that the condition on the inputs, x minus x naught less than delta, implies the condition on the outputs. That's supposed to just be a single absolute value symbol, less than epsilon. My goal here is to prove the contrapositive. So that means I want to deny the conclusion and show that the original hypothesis can't be true. Well, this is the conclusion that we've written down here. Our hypothesis is that the function is continuous. And we want to show that the conclusion is false would imply that the original hypothesis is false. So what I'm going to do is assume the negation of this statement. So what is the negation of this statement? So the negation of, for all epsilon greater than 0, there exists a delta greater than 0, such that x minus x naught less than delta implies f at x minus f at x naught is less than epsilon. So this is the negation. The statement above it, this is the original statement. So we want to take the negation. So what's that going to say? Well, for all there exists becomes, it is not the case that for all there exists some. So that means there exists an epsilon greater than 0 such that for all delta greater than 0, it is not the case that x minus x naught less than delta implies f at x minus f at x naught is less than epsilon. Let me put that in brackets, actually. So our original statement is that for all epsilon there exists a delta such that this is true. So if we look at the negation of that, it's not true that for all epsilon there exists a delta. That means there must be some epsilon such that for all delta, our desired implication is not true. Well, what does it mean for an implication to not be true? Well, let's see. Here we have there exists an epsilon greater than 0 such that for all delta greater than 0, we have what? Okay, the implication says that x minus x naught in size less than delta implies this distance between the outputs is less than epsilon. If this implication is not true, then that means we can have the input values less than delta apart, but the output values are not less than epsilon apart. So that means we have x minus x naught in size less than delta, and also f at x minus f at x naught is greater than or equal to epsilon. So this is the negation right here. It's not true, the claim here is that it's not true that the inputs being within delta of one another implies that the outputs are within epsilon of one another. If that's not true, then there must be some input x such that x minus x naught is less than delta, but also it's true that the outputs are not less than epsilon. So they're greater than or equal to epsilon. So that must mean there must be some x such that this is true. Okay, so this is what we're going to assume. Assume this. And our goal is to show that the function is not continuous. Okay, that's our plan. So let's do that. So as you can see, I've rewritten the contrapositive here or I've written the negation rather here in English rather than in symbols. So there is some epsilon greater than 0. There's some epsilon greater than 0, such that for every delta, there is some x such that this condition is true. So the distance between x and x naught is less than delta. The distance between the inputs is small, but the distance between the outputs is too big. All right, well, we'll apply this fact repeatedly using different values for delta, because the statement is that this is true for every delta. So what we're going to do is we're going to use lots of different deltas. And in fact, we're going to use delta equals 1 over n for every n. So for each n in n, we're going to have an x that corresponds to that delta. So we're going to look at delta equals 1 over n, and for that delta there's going to be an x. So we're going to label it xn to indicate that it's attached to that particular delta. So for each n, we pick one of these x's, x of n, and it has the property that xn minus x naught in size is less than that delta, which is 1 over n. But the outputs are too far away from each other. That is, the distance between them is greater than or equal to epsilon. Okay, so what does this do for us? Well, it constructs a sequence xn. For each n we have an xn, and it always satisfies this condition. Xn minus x naught is less than 1 over n. As n goes to infinity, 1 over n goes to 0. So that means that the distance between xn and x naught is going to 0. So in other words, xn is converging to x0. However, f at xn does not converge, which we can write like this, I suppose, to x0. Because these terms are always greater than epsilon, greater than or equal to epsilon from f at x naught. So that means f at xn cannot be converging to f at x naught. So you have a sequence which converges to x naught, but the f at xn's do not converge to f at x naught, and so the conclusion is that f is not continuous at x0. That's what we wanted to show. We wanted to show that our original hypothesis was false. That's what it means to show the contrapositive. So now what we want to do is we want to show the other way. So we're going to suppose that f does satisfy the epsilon delta criterion at x naught, and then show that f must be continuous. So to that end, we let xn be a sequence in D that converges to x naught. So xn converges to x naught, and we want to show that f at xn converges to f at x naught, because that's what it means for a function to be continuous. Xn is a completely arbitrary sequence which converges to x0. All right, so what is our objective? We need to show that given any epsilon greater than 0, we can find some n, some capital N, such that the distance between f at xn and f at x naught is less than epsilon for all n larger than that n, so n sufficiently large. We're assuming that it satisfies the epsilon delta criterion, and we're going to use that to show continuity. All right, so let epsilon greater than 0 be given. We assumed that f satisfies the epsilon delta criterion, at x0. So there is some delta greater than 0 such that the distance between the input values being less than delta implies, or forces if you want to put it that way, that the output values are less than epsilon in distance apart from one another. Okay, the sequence xn converges to x0. So what does that mean? Well, that means that there exists some capital N such that the distance between the terms xn and x0 is less than delta for all n greater than or equal to n. We know that xn converges to x0. So that means for any, what we would normally call epsilon, but epsilon's taken up. So for any epsilon, we would say that the distance between xn and x0 is less than that epsilon. But like I say, we've already got an epsilon doing something else. So let's call it something else. We'll call it delta. Well, where did we get that delta from? We got it from right here. The idea here is that xn is converging to x0. So that means the distance between these terms is getting arbitrarily small. We can make it as small as we want. Okay, so in that case, let's make it smaller than delta. We're choosing to make it smaller than delta. We know that xn is converging to x0, so we can make the distance between them as small as we like. So what would we like? We'd like the distance between them to be less than delta. And that will happen eventually when n is sufficiently large. How do you say that in a precise way? You say that there exists some capital N, so that whenever little n is greater than or equal to capital N, the distance between the terms is as small as you wanted. In this case, we wanted it less than delta. And the reason we wanted it less than delta is because we know that if the distance between x values is less than delta, that implies that the distance between their corresponding outputs is less than epsilon. So, since these x's, the difference between those x's is less than epsilon, the difference between, or the distance between their outputs is less than epsilon for all n greater than or equal to n. But that's precisely what it means to say that the sequence f at xn converges to f at x0. This is true for any sequence which converges to x0, and so f is continuous at x0. So what we've shown is that if you assume that the function is continuous, then you must satisfy the epsilon delta criterion. But also, we've just shown that if you assume the epsilon delta criterion, then the function must be continuous. So these two notions are equivalent. We can extend this a little bit. Remember that we have a second notion of continuity, which is uniform continuity. So is there a way to describe the epsilon delta criterion that would give us uniform continuity instead of just pointwise continuity? And it turns out that there is. A function f from d to r is said to satisfy the epsilon delta criterion. So this is supposed to say criterion here. On the domain D, if for every epsilon greater than 0, there is a delta greater than 0, so that f at u minus f of v is less than epsilon whenever u minus v is less than delta. All of this in absolute values, of course, for any u and v and d. So what this is telling us is you're going to specify the epsilon greater than 0. So that comes first. For every epsilon greater than 0, you can find some delta greater than 0, so that any time u and v are elements in the domain, with the distance between them less than delta, that forces the distance between their outputs to be less than epsilon. The point here is that there's no restriction on what u and v are, other than they're really close together. We're not looking at a specific point, we're just looking at any points in any 2 points u and v in the domain. So if you grab any 2 points anywhere in the domain, if they're within delta of one another, then their outputs are within epsilon of one another. And that's what it means to be, well, I was about to say that's what it means to be uniformly continuous. We'll see that that's true. That's what it means to satisfy the epsilon delta criterion on a domain. And we're going to show that that means that the function is uniformly continuous. And that's what we're calling the epsilon delta uniform continuity principle. A function f from D to R is uniformly continuous if and only if it satisfies the epsilon delta criterion on the domain D, on the whole domain. So we're not looking at just a single point, we're looking at any 2 points in the domain which are close enough to one another. So a function f from D to R is uniformly continuous if and only if for every epsilon greater than 0 you can find some delta greater than 0 such that the distance between u and v being less than delta implies that the distance between their outputs is less than epsilon. So the proof is similar to the proof of theorem 1, and so we're going to leave it as an exercise. Let's talk now a little bit about 3.6. 3.6 is about monotone functions and inverses. We're going to talk mostly about monotone functions now, and we'll leave inverses for the next lesson. So what do we mean about a monotone when we talk about a monotone function? All right, let's define it. A function f from a domain D into R is called monotonically increasing if f at v is greater than or equal to f at u whenever v is greater than u, that in the domain. That is to say, if you know that v is greater than u, then the outputs must share the same relationship. F of v is greater than f of u. That's what it means to be monotonically increasing. We call f monotonically decreasing if f of v is less than or equal to f of u whenever v is greater than u. So we're assuming that v is bigger than u, and then the outputs have the opposite relationship. So f of v is less than or equal to f of u. If f is either monotonically increasing or monotonically decreasing, we call f a monotone function. This terminology should sound familiar because we've encountered it before in the context of sequences. Now remember that sequences are really functions where the domain is the set of natural numbers. So a monotone sequence is a monotone function where the domain is n, the set of natural numbers. Monotone functions have some very nice properties, and we're going to look at one of them here. This theorem says that if a function is monotone and its image is an interval, then it is continuous. Now this is quite a shocking statement at first because we're talking about a function and all we know about it is that it's monotone and that its image is an interval, and from that we're concluding that it's continuous. This is the conclusion. Normally, we assume that a function is continuous and then we say something about it. But here we're actually saying that if you have a monotone function whose image is an interval, it must be continuous. So how are we going to prove this? Okay, well, let's take a look at the proof. So we're going to start with f, a function from D into R, and we're going to assume that it's monotone, and we're going to assume that its image is an interval. Our objective is to show that f is continuous at every point in the domain. So we're going to proceed using the epsilon delta continuity principle. That is, we're going to show that it satisfies the epsilon delta criterion at x naught. So, to that end, let x naught be a point in D. We want to show that it satisfies the epsilon delta continuity principle, so that means we have to start by specifying an epsilon greater than 0. Well, we're not specifying it, it's arbitrary, it's given to us. That's our starting point. We have a point x naught in the domain, and we want to show that it satisfies the epsilon delta continuity principle. Okay, so in order to do that, start by saying let epsilon greater than 0 be given. Okay, what do we want to do now? We want to show that there is some delta so that the distance between f at x and f at x naught is less than epsilon whenever the distance between x and x naught is less than delta. That's what we want to show. Now, I've rewritten it here in a slightly different way. This inequality right here, or perhaps let me just change the color. This inequality, I'll just underline it, is the same as this inequality. To say that the distance between f at x and f at x naught is less than epsilon is the same as saying that if you look at their difference, it can be no more than negative epsilon and no less. Wait, no, I'm saying that backwards. It can be no more than epsilon, and it can be no less than negative epsilon. Their difference has to be between epsilon and negative epsilon. That's what we mean when we say the absolute value is less than epsilon. That means the actual difference is between epsilon and negative epsilon. We can also rewrite this condition on the x's, this delta condition. We're saying that the distance between x and x naught is less than epsilon, so that means that their difference is between delta and minus delta. So that's what we're going to show, and we're going to use the monotone property of f to do that. We also need the output, the image, to be an interval. That's crucial in making this work. We know that the image is an interval, so let a and b be real numbers such that f of d, well, we don't know what kind of interval it is. We don't know if it's an open interval or a closed interval. We don't know if it includes 1 or 2 or none of the endpoints. But we know that it's an interval. So that means that f of d is equal to either the open interval or the closed interval, or an interval that includes a but not b, or b but not a. These are the only options. So what we know about f of d is that it at least contains or is equal to the open interval ab, and it's contained in or possibly equal to the closed interval ab. So we know that much for sure. All right, this is important. This means that for any c in between a and b, there is necessarily an x in d such that f of x is equal to c. That's what it means for the image to be this interval. It means that for any point inside the interval, there is necessarily an x in the domain such that f of x is equal to c. This interval AB is in the domain. It might be equal to the domain. It might, the domain, or excuse me, it's in the image. This interval AB is necessarily in the image. The image might include A and B as well, we don't know. But we know that this open interval from A to B, that's necessarily in the image. So that means if you pick anything inside that interval, there must be something in the domain that gives you that as an output. Otherwise, it wouldn't be in the image. That's just the definition. Okay, we're going to make use of that fact. Very soon, in fact. All right, so what we want to do is we want to show that we can find some delta so that if all of the x values are within delta of x naught, then the output values are within epsilon of this value, f at x naught. And the argument that we use is slightly different if we're actually at an endpoint. But we don't even know if an endpoint is possible. So let's start by assuming that we're in the open interval somewhere. So we're going to suppose that f at x naught is in this open interval. Okay, so that means if we draw a picture, let's say A is here, and let's say B is here. F at x naught is somewhere in this interval. It's not A or B. It's somewhere in here. So let's just pick this point, and let's call that f at x naught. Now, what that means is I can necessarily find some interval that contains f at x naught at the center, which is entirely in the open interval from A to B. So the way I phrase that here is I let eta, so this is the Greek letter eta, I'm going to let eta be a length so small that eta is less than the distance between f at x naught and either endpoint. In some sense, we could just choose it to be, we could say that it's just, we could specify which one was closer. We could say, assume that A is closer or assume that B is closer. And we just want eta to be some distance smaller than that closer distance. But that's what this says. We look at the This one, b minus f at x naught, b minus f at x naught, that's this distance right here. And then we have f at x naught minus a, and that's this distance right there. So what we want to do is we want to choose eta smaller than the smallest of those distances. So that means we can find an interval with f at x naught in the center, and we can make it so that this distance is eta. Eta. This distance is eta. Should at least try to keep those at the same height, roughly speaking. There we go. So we want to make that distance eta. So the length of this interval is 2 times eta. It's extending from the center. The center is f at x naught, and it's extending in either direction, eta length. Now we want to just choose eta so small that we can be sure that this interval is completely contained in the interval from a to b. Actually, we want it to be a little bit smaller. We want to make sure that it's less than epsilon. So we also want eta less than epsilon. We don't really know how big epsilon is. Epsilon might extend all the way out here like that. That might be epsilon. And so then we don't need to worry about it. But it's entirely possible that epsilon is, let's say here, this length. Well, that's not. This length is epsilon, excuse me. And we're going to go this direction as well. This length is epsilon. So let's find yet another color here. So this is epsilon. That's our little interval. So the idea here is we want to show that if you can choose some delta so that x minus x naught is within delta, then all of the outputs are necessarily within epsilon. So we want to show that there is some delta, so that if the inputs are within delta of x naught, then the outputs are necessarily in this interval. Now we're going to actually do something a little bit better, because we're going to assume that it's in this interval here, this smaller interval. We're just making sure that it's sufficiently small that the interval is completely contained within this interval determined by the epsilons, within epsilon of the center. But we also want to make sure that it's within this interval from a to b. It's entirely possible that epsilon is so large that it's out here, and that's why we want to make sure that the interval is contained completely in the interval from a to b. So that's why we have these conditions here, and also we want to choose eta to be less than epsilon. Okay. Now here I've just written it out again. We want this interval centered at f at x naught extending out from a length epsilon on either side. We want that to be completely contained in AB, which is in turn contained in the image of our set. So any number within eta of f at x naught is in the image of f. Okay, so that's the technical part, or at least that's one of the technical parts here. Now here I just mentioned when choosing eta, we want to just make sure that it's small enough so that eta is less than epsilon is also true. Okay, so what we're going to do is we're going to pick C1 and C2 in this interval so that a C1 is between f at x naught and f at x naught minus eta, and C2 is between f at x naught and f at x naught plus eta. Now this is a lot easier to see in terms of the picture. Let me just redraw the picture for you. Let's just draw it here. So here's A, and here's B. And f at x naught is somewhere in here. We don't know where it is. Let's just say it's here. And we're choosing some eta like so. Like that. So this length is eta, and this length is eta as well, like so. Now what we want to do, well, let's just denote this point right here. That's f at x naught plus eta. And this one right here, that's f at x naught minus eta. So all we're doing now is we're going to choose a point C1 that's to the left of center, but in this interval. So we're going to just pick any C1 right here. And then we're going to pick a C2. Let's change the color. We're going to pick a C2 over here somewhere. It doesn't really matter where, just there's a C2. So C2 is to the right and C1 is to the left. Okay, but we're still in this interval. We're in this interval here. Okay, so C1 and C2 are within eta of the center, f at x naught, but C1 is to the left and C2 is to the right. Now, here we're using the fact that the image, in this next statement, we're using the fact that C1 and C2 are in f of d, the image of f. And we know that that's an interval. We know that f of d is an interval. So any number within eta of f at x naught is in the image of f. And this is where we're using that. C1 and C2 are within eta of f at x naught. So that means they're in the image of f. C1 and C2 are in the image of f. So that means we can find numbers x1 and x2. So we can find a number x1 so that f at x1 is C1. And we can find a number x2 in D so that f of x2 is C2. So this right here, that's C2. And this right here, that's C1. All right. F at x1 is that point, and f at x2 is that point. Basically, the idea is we're just trying to ensure that the outputs are close to f at x naught. And now we're going to use the fact that f is monotone. What is it that we know? We know that f at x1 is less than f at x naught is less than f at x2. But since f is monotone, the only way that that can happen is that x1 is less than x naught is less than x2. Well, that's if f is monotonically increasing. Let's just make a little note here. It would be the reverse. x2 is less than x naught is less than x1 if f is monotonically decreasing. So I'm going to just continue here assuming that f, let's just assume that f is monotonically increasing, but you can see how we change it if it's monotonically decreasing. It's essentially the same, you just change the order of all the inequalities. Now, we're going to let delta be the minimum distance between x naught and x1 and x2 and x naught. Again, I'm assuming that the order of the inequalities is like this. So what we're doing now is we're looking at, let's just draw our number line again. So this is x1, and this is x0, and this is x2. So what we're going to do is we're going to pick delta to be the smallest of the distances here. We're going to look at the distance between x1 and x0, and the distance between x0 and x2. Whichever one's smaller, that's your delta, which in that case looks like this one, delta. And again, if f was monotonically decreasing, you would just put x2 over here and x1 over here, but otherwise it would be the same. Okay, and then you just have absolute values here to make sure that everything's positive. Okay, so if x is in D is chosen such that x minus x naught in absolute value is less than delta, what does that mean? Well, if x minus x naught in absolute values is less than delta, that means the distance between x and x naught is less than delta. So in particular, that means that x is in this interval somewhere. X is in here somewhere. We don't know where, but it's in there somewhere. So we can be sure, in particular, that x1 is less than x is less than x2. Now, again, if f is monotonically decreasing, you just switch the order of the inequalities. But now we use the fact that f is monotone again. And so if we know that x1 is less than x is less than x2, then the fact that f is monotone, or monotonically increasing in this case, gives us this. Now, if f was originally monotonically decreasing, these inequalities would be reversed, but then we'd be using the fact that f is monotone again to get back to this statement. So this one would still be in the same order regardless. Okay, so f, so this is so again we're using, or let's say assuming, well, so we're assuming, or we're using it as monotonically increasing. We are saying monotonically increasing, but we're just doing that just to make it easier to write down. So just to make it easier to write down. To write it out. But remember, if f was monotonically decreasing, then these inequalities would be reversed. But then the fact that f is monotonically decreasing would mean that we'd have this inequality as it is here. So regardless of monotonically increasing or decreasing, you end up with the same inequalities. So what does that mean? That means that you have that f at x is between f at x1 and f at x2. Okay, well, f at x1 is bigger than f at x0 minus eta, and f at x2 is less than f at x0 plus eta. So in particular, that means f at x is between these two. F at x is within eta of f at x0, but remember, eta was chosen to be smaller than epsilon. So if f at x is within eta of f at x0, that means it's certainly within epsilon of f at x0. But this is just another way of writing minus epsilon is less, let me just write that again, minus epsilon is less than f at x minus f at x0 is less than epsilon. And that's itself is just another way of writing the absolute value of f of x minus f of x0 is less than epsilon. So that means the function is continuous. If we choose delta to be given by this distance here, then anytime you have an x and d such that x is within delta of x0, it follows that the output f at x is within the epsilon of f at x0. And that's exactly what it means to satisfy the epsilon delta criterion. And that's what it means, and that means that it's continuous by the epsilon delta continuity principle. Now we only did case 1, but case 2 is actually similar. In case 1, we were assuming that f at x0 was in the inside of the interval, so it wasn't an endpoint. In case 2, we can suppose that f at x0 is one of the endpoints, either a or b. Well, it can't be both, but one or the other. So we do the same thing. You just choose an eta sufficiently small. So you have a and b, and suppose, for example, that we have f at x0 is b. So that means that this one right here is f at x0. Then you want to just choose an eta so that if you find f at x0 minus eta, so this distance right here, that distance is b minus a. So you just want to choose a distance, eta, which is smaller than that, smaller than the interval and smaller than whatever epsilon is. So if this right here is b minus epsilon, then you just want to choose an eta right here. So that this is b minus eta. So this is eta, and this longer distance right here, that's epsilon. So now you look at this interval right here. And what do you do? Well, you can find a point inside there, and you can call that C, let's say C1, I guess. So you have that C1 is less than f at x naught. But again, this is contained in the image of D, which is an interval. So that means you can find some x1 such that f at x1 is equal to C1. So what have you established? You've established that f at x1 is less than f at x naught, but it's also bigger than this point right here. That point right there is f at x naught minus eta, or b minus eta. Okay. And once you have that, then you can argue exactly as we did before using monotonicity. You just choose the distance between, you just let delta be the distance between x1 and x0. Again, we should put that in absolute values, so we should put this one in absolute values here and here. And so once you have that, you would just argue as you did before. And similarly, if f at x naught is equal to a, then you have the same picture, but you just start at a instead. So you have a number line here, and this is your a, and this is your b, and you just start here. So this is f at x naught. And so then, of course, you just pick this distance to be eta, where this distance is epsilon. You just make sure the eta is sufficiently small. And then you find some C2 in this point right here. Let's just change the color. You just choose some C2 here, and then there exists an x2 such that f of x2 is equal to C2, and so on and so forth. It's the same type of argument. I'll leave out the details. Now, as a closing remark, I just want to mention that if the output, or if the image rather, if the image of f is an interval, but the function is not monotone, then there's no reason to assume that f will be continuous. We need to use both the fact that the function is monotone and that the image is an interval to get continuity. So here's an example, or perhaps you'd like to call it a non-example. We have a function f from -1 to 1 into R. And we're going to define it by this formula. So if x is between -1 and 0, including 0, then the output of x is just going to be x again. So on this picture, here we have y is equal to x here. Now, if you're looking between 0 and 1, then you have y is equal to 1 minus x. This function is clearly not continuous. There's a jump discontinuity at 0. But notice that the image is in fact an interval. It's the interval -1 to 1. Because the smallest you can be, well, you can't actually achieve -1, but you're in this interval right here. You're in that interval right there. So the smallest you can be is approaching -1. You're approaching -1. You don't actually get there. And the largest you can be is approaching 1. Again, you don't get there, you just approach it. But as you can see, you can take on every value in between -1 and 1. So here, f of -1 to 1 is equal to -1 to 1, which is an interval. But f is not continuous at 0. continuous elsewhere, but it's not continuous at 0. So you need both the output to be, or the image rather, to be an interval, and also you need the monotonicity. Here it isn't monotone, it isn't a monotone function, because here it's increasing, but here it's decreasing. So it's not a monotonically increasing or monotonically decreasing function. And that's why the conclusion of the theorem doesn't hold, because the hypotheses are not satisfied.